Today we're talking about finding limits algebraically, and there are a couple of strategies that we need to talk about. First strategy that is always your first go-to that you should try when you're trying to evaluate a limit algebraically is just to use direct substitution. In other words, plug in the value that x is approaching into the function and see if the value of the function exists at that point. If it does, then that's the limit. If the value of the function doesn't exist at that value, then we will be using algebraic methods to simplify the expression if possible. In other words, we will try to factor and reduce. If there's a radical, then we will try multiplying by the conjugate. If there are multiple fractions, we will find a common denominator and combine them and see if that helps us to simplify so that we can plug the value in and evaluate it. If f of x has a fraction within a fraction, you will want to combine the numerator and denominator into one fraction, then invert and multiply to eliminate the complex fraction. So those are some of the different strategies that we're going to be looking at in the examples that are to follow. So, first example. On each of these problems, the instructions just specify to find the limit. And so on A, it says find the limit as x approaches 2 of 3x plus 2. So our first attempt at finding a limit is always just to plug the value into the x's. So 3 times 2 plus 2, 6 plus 2. And we get a valid numeric response. So that is our limit. So the limit as x approaches 2 of 3x plus 2 is equal to 8. For B, this time the limit is x approaches 3 of the square root of x plus 1 over 4. We will start by plugging in the 3. So the square root of 3 plus 1 divided by 4. Square root of 4 over 4, which is 2 over 4, and that reduces to 1/2. C. This time we want the limit as x approaches -1 of x squared minus 1 over x plus 1. So plugging in the -1, I get -1 squared minus 1 and -1 plus 1. So in the top, when I square -1, I get a positive 1. So positive 1 minus 1 over -1 plus 1 gives me 0 over 0. Alright, so 0 over 0 is not a valid numeric response. So when that happens, we need to do some manipulating. So this is an example where I can factor the numerator and see if I can reduce by canceling. So when I do this, guys, I am still working with a limit statement. And so I'm still writing the limit as x approaches -1. I'm just factoring the numerator into x plus 1 times x minus 1. And then I'm going to be able to cancel the x plus 1's on top and bottom. That leaves me with the limit as x approaches -1 of x minus 1. This is still a limit statement. You have to continue to write the limit statement until you actually plug that value in order to evaluate. So that's my next step. I'm going to plug the -1 in. So -1 minus 1 is -2. So the limit as x approaches -1 of x squared minus 1 over x plus 1 evaluates to -2. Alright, for D, first thing I always try to do is just plug the value in. So the limit as x approaches -1. So I'm going to plug in a -1 into each of the x's and then simplify. So in the numerator, -1 squared is 1, -2 times -1 is positive 2, minus 3. In the denominator, -1 squared is a positive 1. And once again, I end up with 0 over 0. Now, there's a special name for this 0 over 0. Whenever you plug in and you get 0 over 0, that's called the indeterminate form. Indeterminate form. Because I can't determine the limit when it's in that form. So I'm changing the form by canceling and reducing, multiplying by a conjugate, combining into one fraction, whatever strategy I need to in order to be able to plug in again and get a valid numeric response. So I need to do some work on this one since I got the indeterminate form. So now the limit as x approaches -1, and I want to factor my numerator, and that's going to factor into an x minus 3 and an x plus 1. The denominator is x plus 1, x minus 1. So I've got x plus 1's that will cancel on top and bottom. So now I can rewrite my limit statement. The limit as x approaches -1 of x minus 3 over x minus 1. Notice I'm still writing the limit as x approaches -1. You continue to write that until you actually plug the value in to your x's. So I'm going to do that now. So plugging -1 in for x on the numerator and in the denominator, and I get a -4 over -2, which evaluates to a positive 2. So the limit for D is positive 2. Okay. For E, this time I want the limit as x is approaching 0, so I'm going to plug 0 in for all the x's. So I get 0 over the square root of 1 minus 1, which once again is 0 over 0. And if you remember, we call that the indeterminate form. And so we have to do something to get rid of those zeros so that we can plug the 0 into the x's and get a valid number. And so in this case, because we've got a radical, that's an example of when we're going to multiply by the conjugate. And just so happens the radical's in the denominator, so I'm going to be multiplying by the conjugate of the denominator, which would be the square root of x plus 1 plus 1. So I'm multiplying the numerator and denominator by the conjugate. When you do this multiplying by the conjugate, the part of the fraction that didn't have the radical originally, in this case the numerator, leave it in factored form as you're working. And I'll show you why in just a minute. But in the denominator, when you multiply radical times radical, it cancels the radical. Remember when you're multiplying conjugates that your inside and your outside products cancel each other. So I'm going to have an x plus 1 for the first times first, and then I've got a minus 1 for the last times last. Rewrite my limit statement. Keep the numerator in factored form. In the denominator, my 1's cancel and I'm left with an x. And now can you see why I wanted to leave it in factored form? Because now I can cancel those x's, and I now have the limit as x approaches 0 of the square root of x plus 1 plus 1. Now I can plug my 0 in, and I get the square root of 0 plus 1 plus 1, which is 1 plus 1, or 2. So make sure that you leave those values in factored form because you're going to be able to cancel. Alright, let's look at the last example in this section. And we have the limit as x approaches -4. So 1 over 4 plus 1 over -4 and 4 plus -4. Once again, I end up with 0 over 0, that indeterminate form. So once again, I need to do some manipulating. So in this case, because I've got two fractions in the numerator, I want to add those together first. That's my first step. So when it's still a limit statement, don't quit writing the limit. My common denominator is going to be 4x. So I'm going to multiply x over x here and 4 over 4 there. So I get x plus 4 in the numerator. And then all that's divided by 4 plus x. So this is my big fraction bar. This is my little fraction bar. Alright, limit as x approaches negative 4. I'm going to rewrite this as x plus 4 over 4x. And instead of divided by 4 plus x, I'm going to multiply by 1 over 4 plus x. So that you can see that what we're actually working with here now is a factor of x plus 4 in the numerator and 4 plus x, which is the same thing, in the denominator. So those will cancel, leaving us with the limit as x approaches negative 4 of 1 over 4x. Now I plug in the 4 again, or the negative 4 again, and I get 1 over 4 times negative 4, or negative 1/16 for my limit. Alright, we have what's called limit laws, and basically these are just properties that allow us to break limits down into multiple parts. And so let's go through these limit laws right quick. And so, assuming we've got the limit as x approaches a of f of x, and the limit as x approaches a of g of x. So now what's important is that they both have to be approaching the same numeric value for these limit laws to apply. And so if you have these two limits, you can write the limit of the sum of those two functions as the sum of the two limits. Okay, that's one of the limit laws. Works with subtraction as well. The limit of the difference in the two functions is the difference in the limit of the two functions. So it just allows you to break a function apart into multiple pieces. We have a constant multiple. C stands for a constant multiple. Like if you've got 3x, the 3 is the constant multiple. So a constant multiple times a function, if you're taking the limit of that, you can pull the constant out to the front and multiply the limit of the function times that constant, and you get the same value. We also have a limit law that talks about the product of two functions. So if I'm finding the limit of the product, it's the same as the product of the limits. And also for quotients. If I've got the limit of a quotient, it's the same as the limit of the numerator divided by the limit of the denominator, assuming, of course, that that denominator limit's not equal to 0. So these are the limit laws that we're going to use to break complex limits down into smaller limits so that we can evaluate the smaller ones. And then you put them back together. Alright, so in these examples it says that the limit as x approaches 3 of f of x is 2. Okay. And the limit as x approaches 3 of g of x is 0. Once again, notice they have to both be approaching the same numeric value for these limit laws to apply. It says show the use of limit laws to find the following. So when it says show the use of the limit laws, you have to show that you're rewriting these limits before you start evaluating. So the first one is the limit of the sum, so we want to rewrite it as the sum of the limits. So that's equal to the limit as x approaches 3 of f of x plus the limit as x approaches 3 of g of x. Now, this part right here is the showing the use. And if it says show the use and you don't write that, then you did not show the use of the limit laws. Okay, I know that you can usually evaluate these quicker just by looking at them, but if it says show the use of the limit laws, you have to rewrite the statements first, and then you can start evaluating. So the limit as x approaches 3 of f of x, it said was 2. The limit as x approaches 3 of g of x was 0. So the limit of the sum of f and g of x is equal to 2. The next one says the limit as x approaches 3 of the product of f and g. So rewrite it first. The limit as x approaches 3 of f of x times the limit as x approaches 3 of g of x. Now we can evaluate. So the limit as x approaches 3 of f of x is 2. The limit as x approaches 3 of g of x is 0. 2 times 0 is 0. All right, C. C's getting a little more complex. C says the limit as x approaches 3 of x squared times f of x. Well, here's a product, so let's break apart the product first. So it says the limit as x approaches 3 of x squared times the limit as x approaches 3 of f of x. Okay. Well, we were told that the limit as x approaches 3 of f of x was 2. So we can go ahead and put that in. Let's talk about this other limit, the limit as x approaches 3 of x squared. There's nothing in the description that we were given that talks about the limit as x approaches 3 of x squared. But if we go back to the previous set of problems we were working, the first strategy for evaluating a limit is just to plug in the value. So if I plug a 3 into the x squared, I get 3 squared, which is 9, times the 2 gives you a limit of 18. Okay? And then the last one says the limit as x approaches 3 of f of x divided by g of x. That's equal to the limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x. And we said the limit as x approaches 3 of f of x is 2. The limit as x approaches 3 of g of x is 0. And what does it mean when we say 2 divided by 0? Well, 2 divided by 0 is not allowed. We can't divide by 0. So that means that this limit does not exist. Remember, we use D and E to indicate that a limit does not exist. And so this property can't even be used because the limit of that denominator is 0, so that property does not hold. So your first strategy, always plug in. If plugging in gets you 0 over 0, which is your indeterminate form, then you start manipulating your expression so that you can do some canceling, reducing, and then try to plug in again. Don't forget to continue to write your limit statement every time you do some simplifying until you actually plug your x value in. Then you don't have to write limit anymore.